Hello everyone. In this video we are going to discuss plasma as fluid. Okay, plasma as fluid. So I would like to request you watch the video which is made on single particle motion in plasma. Okay, before you watch this, so link is provided in the description box. Now when we study the plasma as a single particle, then it cannot explain all the properties of plasma. So that's why we need to study plasma as fluid. Okay, so let me remind you the equation of motion when plasma was considered as single particle in presence of electric and magnetic field. Okay, equation of motion of a single particle in plasma in presence of electric field and magnetic field. Okay, that equation is m dv by dt is equal to q into e plus v cross b. Okay, so this was the equation number 1, where v is the velocity of the particle, m mass of the particle, q charge of the particle, now you see, instead of considering single particle, now we will consider plasma as fluid. Suppose this is a chamber containing plasma. It contains plasma. Okay, so here we will consider a unit volume of plasma. Okay, unit volume of plasma, and it contains n number of particles. Okay, and also we have assumed it consists same kind of, or you can say one kind of particles. We have considered all the particles electrons, all the particles enclosed by this unit volume, the electrons. Okay, so it is moving. We are going to study the motion of this volume element. Okay, volume element. Now you see, as you know, ions are heavier than electrons, so ions are considered to be in the state of rest with respect to the electrons. Electrons are in motion, so that's how we have considered here. So we have considered this volume element enclosed electrons. Okay, electrons only, and number of particles per unit volume be n. Okay, and we have considered there is no collision, no thermal motion. Okay, so what we have assumed here, so now first of all let us write here, let us consider plasma as a fluid. Plasma as fluid. Okay. Also, let us assume we'll assume three things here. No collision, next no thermal motion, so what does thermal motion mean? Thermal motion means motion of microparticles, random motions of microparticles. Okay, these particles can move in this direction, that direction, that direction. So this is random motion of microparticles. This is nothing but thermal motion. Okay. Number 3, all the particles in the volume element are of one kind. So say electrons, we have considered all are electrons. Now you see, let us consider n be the number of particles per unit volume. Okay, then you see, if m is the mass of each particle in this volume element, and it contains n number of elements. Okay, it contains n number of particles. This volume element contains n number of particles, therefore mass number is given by m into n. Okay, if we write the same equation number 1, equation of motion, for this volume element, okay, it can be written as, instead of m, now we will write mn dv by dt is equal to, now total charge will be this q. You see, this q is the charge of one particle, so as there are n particles, so qn will be the net charge, then E plus V cross B. This is equation number 2. Let me scroll up the page. In this case, V doesn't represent velocity of one particle. It represents average velocity of the particles in the volume element, and it is assumed to be equal to the velocity of the volume element. Okay, now let us assume, or let us consider, let z x t, x is the position, t is the time, okay, be any physical property of the fluid plasma in x direction, then the change in z with respect to the time t is given by, let me scroll up this, dz by dt, that's going to be equal to del z by del t plus del z by del x and del x by del t. Okay, because it is function of x and t, so that's why we need to find the partial derivative of z with respect to t and that of z with respect to x. Then as it is changing with respect to time t, so that's why we have to multiply del x del t with del z del x. Okay, hope it is clear. Okay, now you see del x del t represents change of position with respect to time t, which means it is velocity along x direction. So that's why it can be replaced by Vx. So we can write del z del t, del z by del t plus del z by del x Vx. Okay, so this is one dimensional. So this is equation number suppose 3. So in 3D, in case of 3D, the change in z, that means the physical quantity x, y, z, its position will be represented by x, y, z now, and t is the time. Change in z with respect to time t, with respect to time t is given by del z by dz by dt, del z by del t plus, here in 3 dimension the velocity, there must be 3 components of velocity, vx I cap plus vy j cap plus v z y cap, k cap, okay, into del x plus del x I cap plus del y j cap plus del z k cap of g. Okay, so this can be written as, let me scroll up the page, this can be written as del z by del t plus v dot del z. Okay, this is equation number 4. So where del means del x I cap plus del y j cap plus del z k cap, and this equation is known as convective derivative. Okay, this is known as convective derivative. So now let me rewrite the equation number 2. Okay, so let me scroll up. This is the equation number 2, isn't it? So let me copy it. Okay, Okay, so this is our equation number 2. Okay, so now you see here, if we consider this physical property g is the velocity of the fluid. Okay, considering g with the velocity v of the fluid, then del v by del t must be equal to, from equation number 4, dv by dt must be equal to del v by del t plus v del v. So this is suppose equation number 5. Now you don't have to write this equation here, equation number 2. It is written above already, so it is hidden, that's why I have written here. Okay, so let us use this equation number 5 in 2. Okay, using equation number 5 in equation number 2, we get, as you can see, this is dv by dt, this is also dv by dt in equation number 2. Replace this, so doing so we will get m, and let me scroll up the page. Okay. Del v by del t, del v by del t plus v dot del into z, sorry, not z, here it is v now. Okay, it must be equal to this part. Okay, q n e plus v cross b. This is equation number, suppose, 6. Okay, so this is the equation of motion, this is the equation of motion of plasma fluid when there is no thermal motion. Okay, no thermal motion. Okay, now we see, when we will consider the thermal motion, when the thermal motion is taken into consideration, when the thermal motion is taken into consideration, then what will happen? Due to the random motion of the particles, there will be a change in pressure. Okay, then there must be a change in pressure. Okay, then equation 6 becomes, because of the addition of the pressure terms, change in pressure. Okay, this equation becomes, so let me scroll up, mn del v by del t plus v dot del into v is equal to qn plus v cross p minus del p. Okay, so here p represents pressure and del p represents change in pressure. And why it is negative? It is negative because you see, suppose this is a ball contains fluid, it contains fluid. Okay, it is a ball containing fluid. When you will apply a force here, then pressure due to this fluid will be in the direction opposite to the force. That's why it is negative. Okay, so hope you have understood this. So this is the equation of motion. This is the equation of motion of the plasma fluid when the thermal motion is taken into consideration. Okay, so hope you have understood this. So thank you for watching. If you like my video, then please share my videos and subscribe the channel if you are new to my channel. So thank you.